All right, so hello everybody. Today we're going to be starting what's sort of Unit 2 in this class. We've completed our study of data structures, and now we're going to be looking at combinatorial optimization. Now, that's not entirely true because there's going to be an optional lecture on suffix trees on Friday, which I encourage all of you to attend. It's a really fun and interesting data structure, quite useful in practice. But you've seen the last of my lectures on data structures. So we're going to move on to this topic, combinatorial optimization, which is basically poses the problem of finding an optimal solution over some combinatorial space. So we're going to be looking at a lot of problems on graphs, for example, and later we'll look at some problems in scheduling theory and a variety of other topics. But this phrasing of finding an optimal solution really breaks down into three pieces, and I find it quite useful when you're looking at a new combinatorial optimization problem to tackle those pieces one at a time. So the first piece from solution is about understanding what are the feasible solutions. So in the shortest path problem, you have to understand what a path is before you can start talking about shortest paths, right? Once you understand what the feasible solutions are, the next step is generally to understand optimality. You don't jump straight to coming up with an algorithm for finding the optimum solution, but there's often a good waypoint of saying, can you verify the optimality of a proposed solution? So if somebody gives you a solution and says, I think this is the optimal one, can you tell? Can you either find a proof that it is or a demonstration that it isn't? That's often easier than the final step of actually constructing the optimum solution. And so we're going to go through this pattern several times over the course of the next few weeks of defining a new problem, understanding the space of feasible solutions, then understanding what makes an optimal solution before we actually start looking for it. And then finally, with that understanding, we will proceed to algorithms to actually construct the optimum solution. All right? So that's what we'll be seeing for the next few weeks, or maybe even a month. The particular problem that we're going to be starting with is the maximum flow problem, which is really the foundational problem that launched, I think, the whole field of combinatorial optimization the way that we think about it today. All right? And some references if you want to read about it. Tarjan has a very nice little book on data structures and network algorithms. It's quite dated at this point. It doesn't have any of the most recent inventions. I mean, I think he wrote this before he came up with splay trees, for example. But it's beautifully written and provides a lot of clarity on the problems in some of the basic algorithms. The foundational paper is due to Ford and Fulkerson. They sort of invented combinatorial optimization in this paper, which is called Flows in Networks. Which was published in 1956. And then there was a book in 1962. If you want sort of the relatively up-to-date stuff, Ahuja, Magnanti, and Orlin, who are or were all here at one point, have a whole book on network flows. And so that's the reading material that will be relevant for the next couple of weeks. And so now the formulation. In a graph, possibly with capacities, or sorry, you want to find a flow of maximum value. So that's the definition of the problem, only it doesn't really define anything because I haven't said what a graph is, what a flow is, or what the value is. So breaking that apart, we're going to be thinking generally about directed graphs. With a capacity u of e on each edge e. All right. Now, as special cases to that general notion of a directed graph, we may sometimes talk about undirected graphs. But you can always think of an undirected graph as a directed graph, right, where you just sort of replace the undirected edge uv by a pair of edges uv and vu that go both ways. Okay? We may also sometimes talk about what are sort of misnamed uncapacitated graphs, which just mean that all of the capacities are equal. And if they're all equal, you might as well just assume they're all 1 by scaling everything. Okay. Now, you may ask why I'm using U for capacities instead of the obvious C. You'll find out next week. Okay? I'm going to keep you in suspense until then. So we've got directed graphs and their sort of specializations. The graph, in order to define flows, also has, well, so let's move on to that's the graph part. Now let's talk about the flows. So to talk about a flow, we have our graph, and we take a source vertex S and a so-called sink vertex T. And our goal is to assign a flow which puts a value f of e on each edge e, satisfying some important conditions. So the first one is what's called skew symmetry, which just means that what we call the flow from W to V is equal to minus the flow from V to W. So it's the net. So the intuition for flow is of water flowing through the edges and vertices of this graph. And so F measures the amount or the rate of flow through an edge. And F is sort of a net flow measure. So if you've got positive flow from V to W, it means you can equivalently think of that as a negative flow from W to V. The next important criterion, which is satisfied by flows, is what's called, let's save that one for last because it's the hardest, is capacity, which simply says that the flow from V to W is less than or equal to the capacity of the edge connecting V to W. Finally, we have what's called conservation, which says that the sum over all of the neighbors of a vertex V of the flow from V to those neighbors is equal to 0, unless the vertex V that we're talking about is the source or the sink. Right? So those are the three definitional criteria for flow. Yes?
Is the U VW just the sum of the capacities that we
want for? U of VW, this is the capacity variable. Right? So I wrote E over there because I was talking about an edge. Here I'm talking about V and W, which are the two ends of that edge. Okay? Yes?
What if there's only edge one from V to W, but not edge one from W to V? So what do you do with the skew symmetry?
Well, this is one. So there's actually two ways to define flows. They both have their pros and cons. But this one works very nicely because if you think about it, if I have a capacity on the edge from V to W, right? If I don't have an edge at all from W to V, that's sort of like having a capacity of 0 going from W to V, right? Now, if I've got a flow where there's some positive flow going from V to W, whose value F is less than U of V to W, then by skew symmetry, that means that the flow in the opposite direction is negative, right? So if I think of having a 0 capacity in the opposite direction, then that satisfies the capacity condition by being negative. Okay? Good. So people understand the the definitions. I also say if you just have skew symmetry and conservation, you could say that you have a flow. If it doesn't satisfy the capacity constraints, then it's not a feasible flow. It's one that you would need some more capacity in order to carry in the particular network. But generally, when we talk about flows, we're going to be implicitly talking about feasible flows, which means that the capacity condition holds as well. Okay. Finally, we define, if we have a flow like this, we can define the value of the flow to be the sum over all of the neighbors of S of the flow from S to W. Okay? So it's the amount of flow leaving the source of all of this flow. Okay? Now, there's a natural question to ask at this point, in that I seem to have made sort of an arbitrary choice between two equally plausible choices for defining the value of the flow. So it would be an alternative, sort of symmetric notion of the value of a flow. Yes?
Sum over T.
Right. So what about the sum of the flow to T? Right? Why did I pick S rather than T if I have these two distinguished vertices? Well, one of the first things that we're going to show is that it doesn't matter, that they're actually both equal. There's conservation at a higher level in flows that emerges from this low level of conservation. Okay? Now, I'll also mention there's sort of an alternate definition of flow in terms of what you could call the gross flow. So this formulation is very nice mathematically, this skew symmetry. It makes everything is nice and linear, and you can add things to each other, and it all works out. But in practice, you may find it a little uncomfortable to think about negative amounts of water flowing from one vertex to another vertex. You know, all that antimatter, if it hits regular water, you'd have a, it could be bad. So you can think about sort of a gross flow formulation where you talk about the amount of a positive amount of flow on each edge. So you can define sort of a G of VW, which is not necessarily equal to G of WV. Instead, it measures, as I said, sort of it's only there when there is positive flow. So in the usual case, you would have G of VW be positive and G of WV equal to 0, representing that there's stuff flowing from V to W and not from W to V. And then you have to sort of change your definitions a little bit, right? So for conservation, now what you say is that the sum over W of G of VW minus G of WV should be equal to 0 unless V is S or T. Your capacity constraints would now be written by saying that you want positive values on your measuring your flows, and now you don't have the skew symmetry criterion anymore because everything is now forced to be non-negative, and now the value of your flow is the sum of the flow out of S on various edges minus the flow into S on various edges. Okay? And it turns out that these are entirely equivalent definitions, right? If you have a gross flow, you can compute what the net flow that produces is between various vertices and go from G to F. Alternatively, if you have a skew symmetric flow, you just take the positive parts of it, and that gives you a sort of a gross flow formulation. I'm going to use the skew symmetric one pretty continuously through the lecture, but this is sometimes useful for intuition. Yes? No, all the so in the basic flow problem, the one that we're going to be talking about, all of the capacities are non-negative, right? So in general, if you have a directed graph with an edge in one direction and no edge coming back, you'll have a positive capacity in the forward direction and a 0 capacity in the backward direction. You can have positive capacities in both directions, but as we were discussing before, that doesn't force you to have a positive flow in each direction. You can satisfy the capacity condition.
The negative flow, when it comes from the skew symmetry, the negative flow is itself, like if you take it the other way, it's going to be positive and it's going to be less than the capacity. So
exactly. So that's the requirement, right? In other words, if we have a graph like this, right, where we have a capacity of 5 here, then what that is saying is that we have to have the flow in this direction be less than or equal to 5. Now, if we set a flow of value 4 going in this direction, right, then the flow in the opposite direction is minus the other flow. So it would be minus 4 or something like that. But when we do that, we look up and we say, well, there's 0 capacity, but minus 4 is less than 0. So we satisfy the capacity constraints. Okay? Yes?
What is GFW not equal to GFW times?
Oh, this is saying this is allowed, right? In other words, you're not required to have G of EW equal to G of WV. Okay, right? In this, sorry, equal minus. What I'm saying here is that you don't have to obey skew symmetry. Okay. Other questions? Everybody's got the definition down? Yes?
So does the capacity have to be the same in either direction?
No. So that would give you what I'm calling here an undirected graph. Right? If you enforce identical capacities in both directions, then the way to represent that, you don't need a directed graph anymore. You would just take an undirected graph and put the capacity on the undirected edge. But the flow problem is more general than that. It allows distinct capacities in the two directions. They're equivalent. They're completely identical definitions. You're just, again, in one direction you're basically taking off them. You're basically zeroing out the negative values, and in the other direction you're just taking, you know, f of EW minus f of WV, or sorry, G of EW minus G of WV as your net flow. Okay. And since they are equivalent, I don't have to sort of do everything with both. So I'm going to be focusing on this one. Okay. Other questions? All right. So now I've got a definition. So the flow problem has turned out to be incredibly fundamental. There are literally hundreds, if not thousands, of optimization problems that have had to be solved in practice that turn out to be a flow problem in disguise. So knowing how to solve flow problems gives you a tremendously powerful tool for solving all sorts of optimization problems that arise in a very broad variety of areas. The intuition for the flow problem, again, as I said, you can think of it as a flow of water, right? You've got a network of pipes, and you're asking what is the maximum amount of water that can run from the start of the network of pipes out to the other end, to some exit point from the pipes, right? In that case, the flow would be measured in a rate, like liters per minute or something like that, as how much flow can get through a particular pipe and what is the amount of flow per minute that you can send through the entire network as a result. But you can equally use flow to, for example, measure flows of packets on the internet. So how many packets per second can you send through each link, and how much traffic does that allow you to deliver from Netflix to your home theater system, right? So equally applicable there. And so we're going to be looking at the maximum flow problem, which says over all of the flows that satisfy these feasibility constraints, find the one that delivers the maximum amount from S to T. Okay? But as I said, before we start thinking about optimality and how to find an optimal solution, we want to think about feasibility. And so we're going to start actually with sort of a structural theorem, another way of looking at these flows. Okay. So to creep up on that, what would be the sort of simplest example of a flow? Yes? The zero flow. That is an excellent answer, and is exactly the sort of answer that I like to sort of start off with, right? So does the zero flow satisfy all of the feasibility conditions that we have above? Well, assuming all of the capacities are positive, it sure does. Okay, I'll leave it to you to work out the complicated mathematical details. What's the next most simple example of a flow? And here I'm thinking sort of pictorially or structurally rather than numerically. Yes?
Do you ever think the smallest capacity that appears?
So set f of e equal to the smallest, set every edge to have a flow equal to the minimum capacity on the network. So that will certainly satisfy the capacity constraints. Is it going to satisfy everything else? I see shaking head. Why not?
Because of the other condition.
Which one breaks? Yes, right? There's no requirement in a network that you have the same number of incoming and outgoing edges. And so if you have a graph that has a vertex like this, then setting everything equal doesn't work. Okay? But suppose I just wanted to get some flow from point A to point B. What would be sort of a natural, simple way to do that? Yeah?
Choose a path from S to T.
A path, right? A path from S to T, right? I can walk along that path. How much capacity can I put on that path without violating, or how much flow can I put on that path without violating feasibility? Yeah?
Just the minimum capacity.
Yeah, I'll just look for the minimum capacity of an edge on the path. I'll set the flow value equal to that capacity on equal to that amount on every edge on my path. Does this give me a feasible flow? Well, we've just arranged for it to satisfy capacity. Does it satisfy, and so again, I'm telling you how I set the positive flow in the forward direction. That is implicitly setting negative flow in the reverse direction thanks to the skew symmetry, but we won't worry about that because negative flow values don't violate the capacity constraints. The question is, does this satisfy feasibility? Or sorry, does this satisfy conservation? Yes. How come? Yeah?
There's a flow at that condition, there's also flow path leaving.
Exactly. At every vertex, there's some flow coming in on the incoming edge of the path, but there's an equal amount of flow going out on the outgoing edge of the path. And so again, if we go back to the skew symmetric representation, what we would really say is that the incoming flow from a vertex x to v, right? That's a positive flow from x to v, but that means it's a negative flow from v to x. And that is canceled by the positive flow from v to the next vertex on the path, so that the sum of the flows to v is 0. Okay? Good. So a path is a good representation of, is a good example of a flow. But it turns out that in fact, paths are all that are going on with flows. Okay? So here's a very nice little lemma called the path decomposition. It says that any ST flow, and this is actually true regardless of whether it satisfies capacity constraints. This is just if it's a flow, if it has conservation, okay, then it can be decomposed into, well, what I just said, ST paths carrying flow. But it turns out that that's not quite enough to cover the full decomposition. We also have to allow for cycles carrying flow. All right? And we need those cycles because sometimes there's wasted work going on in a flow where stuff is just going around in a circle without ever getting anywhere. Okay? It's never really necessary to have those cycles in max flow, but they can exist. Yes?
Can an edge be unique in one of those paths?
We can limit it to simple paths and cycles. Okay, as we will see from the proof. Okay. So, how do we prove this? Right? Yes.
What do you mean by simple?
There's no repetition of vertices or edges on the path, right? I mean, a path that has a repeated vertex is just one that contains a cycle. So you can take out the cycle. A cycle that has repeated vertices is just 2 cycles. You just sort of can keep breaking it apart. Okay?
So
Yes?
I meant if the same edge can appear in 2 different paths.
Absolutely. And that's very important. So this is not a disjoint decomposition where you assign every edge to just one path. Instead, you may need to have several different paths that all use the same edge and then go off in different directions. Okay? All right, so how do we prove this? How might we start to prove this? So what we need to do is, it's a decomposition problem. And in general, in these kinds of decomposition problems, instead of trying to decompose everything at once, you take the simpler goal of, can I find one of the things that I want to decompose into, right? So I've got this flow. Can I take out one path from the flow? If I come up with some procedure for taking out one path or one cycle from the flow, well, then I just iterate that procedure, and eventually I'll have taken everything apart, right? So the question is, how do we find a path or a cycle? in a flow. Yes?
Just take an edge that has positive, that has outward flow, follow it, and keep following edges.
Okay, so let's break that down a little bit. Take an edge that has positive flow, but do we take an edge from anywhere? Good, from the source. So start at S, and let's find an outgoing positive flow edge. Now, can we always do that? Yeah?
If the total flow is, if the value is positive, then yeah.
Okay, so if the value is positive, the claim is that we can find a positive outgoing flow edge, right? So, I mean, let's look at the reverse of that first because it's easier, right? Sorry, no, let's just look at this. So, if we have a positive flow, why can we find an outgoing positive flow edge? Yes, Parker.
So that the value is the sum of the outgoing flows from the source, and if it's positive, then at least one of them has to be positive.
Great. This is just sort of a law of averages things, right? I mean, you may have some negative values going out of the source. I don't know why you would, but it could happen. But as long as the total flow value is positive, there has to be some edge contributing positively to the outgoing flow. Okay? So we can do this. We can find an outgoing positive flow edge. So what should we do when we have that outgoing positive flow edge? Well, follow it to some vertex x1. Okay. Now what do we do? Yes?
Find the outgoing flow edge from X1.
Why can we? Good. So it's the same argument, right? This comes from the conservation requirement, right? So if I have flow that is positive from S to X1, right, then from X1's perspective, it's a negative contribution to the conservation bound, right? And so I need a positive contribution to balance that in order to achieve a net zero flow at X1. Okay, so we can find an outgoing one, right? So we can obviously keep doing this. And we're going to keep doing it until what happens? Yes?
Until you encounter T or a previously visited vertex.
Good. So one possibility is that you encounter T. So what do I declare if I encounter T?
Get an ST path.
I have an ST path. Right? On the other hand, as you pointed out, another possibility is that I encounter a previously encountered vertex. So what do I declare if I encounter a previously encountered vertex? That's a cycle. Okay. So I can find, using this simple procedure, I mean, this is an algorithm. It's not an algorithm that we need to run right now. We're not worrying about efficiency yet. Right now, we're just trying to understand the decomposition. But this tells us that we can use this algorithm to find a path or a cycle in the graph. OK, that's one path or cycle. How do we take this and turn it into a full decomposition algorithm? Yes?
When you run it once, you get at least one edge that now has zero flow.
Good. So but let's unpack that. What do you mean by getting an edge that has zero flow? Well, I mean, right now I just have a path. What do I do with that path or with that cycle that I've just found?
Subtract it from the edge.
Good. So this is going to be sort of our inner loop. Once we found the path, we are going to want to subtract the path from the flow. But we have to figure out what this means, right? I mean, I know how to subtract numbers, and I need to understand what it means to subtract a path. Yeah?
So we can from every edge, we can remove the minimum edge of the path.
Great. So what that means is we reduce the flow on each path or cycle edge by the minimum value of f of e on the cycle or the path. Right? Now, we have to make an important claim about that if we want to continue with our induction. Right? So if we reduce the flow on each edge of the path by this amount, what is still true of our flow? Yes?
It's still a flow.
It is still a flow. Right? What do we have to check or understand in order to know that it's still a flow? Well, again, the tricky part is the conservation argument, right? But the point is that since we're subtracting a path, right, we're removing incoming flow and outgoing flow from each vertex on the path in equal amounts. So if conservation held before, conservation still holds after, right? So now, although it's not great board technique, I'm going to squeeze this in here. How often, can this go on forever? If we sort of do this subtraction of paths, I mean, decomposing into an infinite number of paths could be problematic if we're trying to do something algorithmic. Yeah?
You get a 0 before on a certain edge, and that number of 0 goes increases.
Great. So this turns some edge to having f of e equals 0. And so that can only happen m times. Right? Yes?
When you subtract by minimum, don't you also need to add on the negative?
Yes. But see, that's sort of implicit in the skew symmetry perspective. Remember, we looked only at positive, we found this path or cycle through the positive edges, right? And so we can say we're subtracting from all of those, and implicitly we're at the same time adding an equal amount to the reverse edge.
And why would you eventually get all the edges to be 0?
So I guess the way to say it is that when I do this transformation, I'm taking some edge that was positive, and I'm making it 0. Yes? If you think about it also in the reverse direction, I'm taking an edge that was negative, and I'm making it 0, because we have skew symmetry all the time. Right? So the positive edge turns to 0. That happens each time I remove a path or a cycle. So how often can I turn a positive edge to 0? Right? And the other important point to notice is that I never take a 0 edge and turn it into something else. Right? Because I'm only taking flow off of things that have positive value. Right? So anything that is 0 stays 0 forever. And therefore, I lose one edge every time, and I never gain edges. So after m iterations, I will have taken out all of the flow. And that actually lets us strengthen our argument, right? Here I said any ST flow can be decomposed into paths and cycles, but what we're actually showing is that it can be decomposed into, at most, m paths and cycles. And that's actually very important for some of the algorithms we're going to develop. Yes?
So, would it not find like some residual cycle that's not connected to like the root?
Good point. So after I run this process, if I do things the way I described here, right, at a certain point I'm going to use up all of the flow out of S. Right? So that there's no longer any positive flow edge coming out of S. But there might still be some positive flow in the graph. So how should I continue this decomposition procedure at this point? Yeah?
You can pick a vertex or something.
Yeah, pick a vertex that has some positive outgoing edge and start there. Okay? And I'm going to work forward, right? Until I get to I'm going to, at that point, because the sort of the flow is, how to say it, all that's left is cycles. So I'll actually come back and hit myself at some point as I am following things out. Okay. But you might object to that argument, right? So why can I be confident that I will only find cycles that way? Is it possible for me to, start in the middle and finish at t? Yeah?
So this would violate the conservation.
Would it? How come?
The first one had a positive flow out, but nothing in there.
Well, I didn't say, I mean, you could imagine, let's do this pictorially, right? I start at x, I go out, I follow a chain of positive flows, and I get to t. And at that point, you know, t doesn't have a conservation requirement. So it may not have any outgoing flow. So what should I do? Yeah?
So if you take the sum of all the flows, you're guaranteed that that's 0.
The sum of all the flows.
Skew symmetric, right, of all the pairs.
Okay.
If you group them by the conservation,
Mm-hmm.
you know that you're going to be left with all zeros except for the sums of the s and the t. So
Mm-hmm.
it's be equal.
Good. So what you're doing is jumping ahead to a proof that, in fact, the flow out of S is equal to the flow into T. And that happens by just summing all of the different conservation formulas. Okay? But I'm actually going to prove that from the path decomposition, okay? Because I hate algebra. For me, it's all about the combinatorics. So I don't want to do summing formulas if I don't have to. So how might I address this from a combinatorial perspective or from an algorithmic perspective? The worry is that there's some flow coming into T that catches me. Yeah?
If you deleted all the flow from T, there's actually conservation.
So you're making the same argument. So I want to get to that argument instead of relying on it. Yeah?
So X has a conservation of flow, and in this path, all those nodes have the equal incoming and outgoing.
Mm-hmm.
So there still has to be an incoming.
Good. So you're going to argue that if I'm able to do this, there has to be an edge coming into X, right? Because X has conservation of flow. Right? So I can sort of work backwards from X using the same sort of conservation argument, right? So I'll work forward from X until I hit T, maybe. I'll work backwards from X. I mean, if I hit T, then I've got a cycle. At some point, I'll have to repeat myself. And at that point, I'll have a cycle that involves X, and so I can take it out. Okay? So that lets me take care of any flow that still remains in cycles. Okay? Other questions? All right, so now we've got our decomposition. And from our decomposition, we can argue we can argue exactly the claim that was just made, that the flow out of S is equal to the flow into T. But we're actually going to prove something a little bit more general. Okay. So now that we understand something about the structure of these flows, that really they're just glorified paths, right? They're just combinations of paths and cycles. Let's move on to the decision question. So I'm still not thinking about optimization. But let me ask the question, can you look at a graph and decide, is there a non-zero feasible flow?
All the edges to T, are they all in flows? Like, are they all directed?
That's not required in the definition of a flow.
For S either.
That's right. It's not required. Now, it turns out that if you remove all the outgoing edges from T, it doesn't change the results of your problem, but we have to prove that. Yes?
So if there is a path from S to T, then we can
Great.
just pick the minimum.
So if we want to ask whether there is a non-zero feasible flow, an obvious question to ask is there a path? So if there is an ST path with positive capacity, then yes, there is a feasible flow that is positive, right? We just discussed that. You take that path, you put the flow on that path, and you're done. But this is only a one-way if, right? To really understand something, we need an if and only if. So what do we still want to prove in order to understand about non-zero feasible flows?
There's no path and there's no flow.
Right. So the tricky part, right, this was obvious, but can we say that if there is no ST path, then there is no flow? How do we prove that? Contrapositive, yes. Good. So what we're actually going to say is, so let me finish writing the question. So what we're going to prove is that if there is a flow, then there is a path. Right. How do we prove that? Yeah? So now we invoke our decomposition, right? So we decompose this non-zero flow into paths and cycles. Okay. Now, if there were no cycles in the decomposition, we'd be done, right? This would be easy, right? We've got a collection of paths, and there's a certain amount of flow on each of those paths. Well, and those paths, the sum of those paths, they obeys the capacity constraints, if you think about how we decompose the flow. So we've got, if we have a flow, we have a path which is using edges that have non-zero capacity on them, and so that tells us there is a path of edges with non-zero capacity. Now, does the possible presence of cycles in this decomposition change anything? Yes?
What if there are no paths or missing?
Exactly, right? Maybe I do this decomposition and all I get are cycles. What, right? That would appear to be a problem because I'm not exhibiting any paths. But what's going on if my decomposition is only cycles? Yeah?
Cycles can only contribute 0 t to the sum.
Good. So for this, we go back to the definition of the value of the flow, right? The value of the flow is equal to the sum of all the flows going into and out of S, right? Now, any cycle conserves everywhere. It has the same amount coming into and out of each vertex on the cycle. So it contributes nothing to the value of the flow, right? So cycles don't contribute to the flow value. So if there's a positive flow value, that's going to imply that there exists a path. And so then we're done. We have the path that we wanted, right? I mean, this captures something more generally interesting, right? Again, that these cycles contribute nothing to the flow. If you throw the cycles away, you have a flow of exactly the same value. So there always is a flow of a given value that has no cycles in it, if you want to do the work of finding it. Okay. So now we have this nice characterization, right? That there's a non-zero feasible flow if and only if there is a path. So again, turning that around, right? So if there is no flow, that tells us that there is no ST path. So if we draw our graph, right? We've got S over here, we've got T over here. What does it mean for there to be no ST path? Well, I can look at the edges that have positive flow value on them, right? And I can sort of explore outward from S in various directions, right? And I'll find various edges as I do this, you know, breadth first search, depth first search, whatever I want. What has to not happen if I want to say there's no ST path? Never hit T, right? So in all of this exploration, I'm going to reach a set of vertices that does not include T. So I could draw sort of a boundary and say, well, there are some vertices that S can reach. And conversely, there are some vertices that T can reach. There's probably also some vertices floating in the middle, but I'll just put them on the T side for completeness. Okay. And what I have in the middle is what's called a cut with no positive crossing capacity. So none of the edges going from the S side of this cut to the T side of this cut can have any positive capacity on them, right? Because if they did, then my exploration would be able to cross the cut. And I would be able to pull more vertices into the S side of the cut. Okay. And so this gives us another characterization of the sort of presence or absence of a non-zero flow, right? A non-zero flow is present if I can exhibit a path from S to T. There is no non-zero flow if I can exhibit a cut separating S and T. So in this sense, the path and the cut are duals of each other in a way that will become more clear as we proceed. Okay, so you have one or the other. Either you have a path from S to T, or you have a cut separating S from T. And exactly one of those is true. And that determines whether there's a non-zero flow or not. Okay? We good? Yes?
This is kind of silly. Like, what's the issue with the case where like you have S and T and maybe like 10 flow from, or a cycle that involves S and T?
But you see, if I have a cycle that goes from S to T and back, then how can I use that cycle? Well, I can throw away part of the cycle and have a path that goes from S to T.
I'm saying like in the cycle case there is no flow.
It is, so you have to be a little bit careful. It can be possible to have a flow even when there is a cycle. The argument is that if your whole thing decomposes into cycles, then it's not delivering any flow from S to T. So the example that you just gave of a cycle running from S to T and back, right, the net value of that flow is 0, right, because it's just bringing all the stuff back that it started. But in terms of existence of a non-zero flow, I can take this cycle and just forget to bring the flow back. And now I have a non-zero flow from S to T. So there was a path. I wasn't using it before in my flow, but I can build a flow using that part of the cycle. Okay. Other questions? Yes?
Would the path decomposition in this case?
Yes, because remember, when you do path decomposition, you're not decomposing, you're decomposing a flow, right? So this is a flow of value 0, right? And what path decomposition tells you about a flow of value 0, if you think about it, it tells you you can decompose it into cycles with no paths. Okay, so that's sort of a special case. These flows of value 0 are called circulations for obvious reasons, and we will study them a little bit more next week. They come up in some generalizations of the problem. Yes?
So with the arguments that you'll always get some edge like to go so that f of equals 0, and this can only happen m times.
Yes.
Like, let's say like you so you have some flow that goes on the edge.
Yeah.
And then later you have another flow that goes like, backwards along that edge. Possible. Then wouldn't like.
Well, so this is actually where things start to differ between the skew symmetric formulation and the gross flow formulation. So if you notice, in the skew symmetric formulation, it isn't possible to have flow going both forward and back on an edge, right? The flow is positive in only one of those two directions. Okay? If you think about it in terms of gross flow, right, you can imagine, well, I'm sending 2 units of flow forward and sending 1 unit of flow backwards. But net, you're just sending 1 unit of flow forwards, and that's how you sort of think about the formulation. Okay? Other questions? Good. It's great. I haven't had this engaged a class for several years, so this is nice. Yes?
If I apply this algorithm to the path decomposition of this...
Yes. Then what I'm going to get is a decomposition that consists of 1 cycle and no paths.
Exactly the algorithm. From S to T, I'm going to find 1 path, and I'm going to break the cycle.
Oh, I see what you're saying. Good point. So what I should do is stop at T only if I have to, right? If there's no way to continue, right? So I'll be aggressive. I'll follow the paths until I have to stop. And what's the definition of have to stop? Either I get back to someplace I've been to, or else I get to T and there's no way out. Right? So that's actually a good point, and I should reformulate my algorithm to reflect that. So I'll do that in my notes. Okay. Good. OK, so let's move on. Now we've got this decision condition, this criterion for deciding whether there is a non-zero flow. So now we're moving from feasibility towards optimality, and so let's ask the question, how do we decide if a flow is a max flow? So somebody says, here's a graph, here's a flow. I claim that it's the maximum flow. How can you check? Okay, so I'm not yet giving you the work of finding that maximum flow, but to at least verify that one is maximum is an interesting question. Right? So in most general terms, if you're trying to prove that something is maximum, right, what do you need in order to accomplish that proof, sort of regardless of what the problem is? Yeah? That is one technique that can give you what you need, but that doesn't always apply, right? So in the most general sense, if you want to prove that this is the maximum possible value, what do you essentially have to prove? Yes?
So that every other value is smaller?
Every other bound is smaller. In other words, you need an upper bound. Right? In order to prove something's maximum, you have to prove that there's nothing bigger than that value. So you need to prove that you have an upper bound. And that's what we need to do here is when somebody gives us a flow, we need to argue that the value of that flow is an upper bound on the value of all possible flows. And that we're meeting that upper bound is then how we show that we're maximal. So how do we do that? How do we come up with an upper bound on the possible values of a flow in the network? No fair answering if you've already studied flow. Yes?
Some of the edge weights out of S, or sorry, capacities out of S.
Great. So that is an excellent starting thought for the upper bound, right? We've said that the value of the flow is equal to the sum of the capacities coming out of vertex S. To the sum of flow values coming out of vertex S. We have an edge-by-edge bound that says that the amount of flow is less than the capacity. So certainly the total capacity of edges leaving S is an upper bound on the total flow on edges leaving S, which therefore upper bounds the flow. The problem is that that upper bound is not necessarily tight, right? So can we think of an example of a graph where we have lots of capacity leaving S, but the value of the flow is much smaller? Yeah? Good, not as much flow entering T. So for example, I could have a situation that looks like this. So here's S. Let's make it even worse. Here's T. Right? So lots of capacity leaving S, 4 edges, but only one edge entering T. Right? So there's an instinct that you can't get a lot of flow here. But how do we formalize that instinct? Because this does show a lot of capacity leaving S, and that's where the definition of the value of the flow is. So how do we get a better upper bound than just the edges leaving S? What's the problem with this network? Why can't we get all that flow to T? Yes?
I think the cost is
So you pointed so precisely that I know exactly which cut you're talking about. There's this cut here, right? A separation of the vertices into an S side and a T side. And we see that there's only one edge going from S to T. And so now I can make a general claim, right? So my claim is that the value of the flow F is less than or equal to the value of an ST cut. So pick a cut, look at the total capacity, and so I have to define what value means. So let me say here, total capacity going from the S side to the T side of the cut. Okay, and so if I have a certain amount of capacity going from the S side to the T side on a cut, I claim that upper bounds the maximum flow that I can deliver from S to T. Can we prove that? Physically, it seems intuitive, but how do we formalize? Yeah?
Every path from ST has to go through an edge on the cut.
Excellent. So we again use path decomposition. And again, as we were saying before, cycles are sort of irrelevant here because cycles contribute nothing to the value of the flow. So let's ignore the cycles. They don't matter. The real issue is that whatever the flow is, we can decompose that flow into paths. And the value of the flow on those paths is equal to the value of the flow. The sum of the flow on the different paths in our decomposition is equal to the value of the flow. Right? So we take this path decomposition, and now we know that every path must cross the ST cut. Okay. And I kind of tossed this off, but this was actually a really big problem in 19th century mathematics, like the Jordan curve theorem and stuff. They got stuck for a while because they couldn't prove that things had to cross other things. But since we're doing finite, discrete mathematics, I'm not going to worry about it. Obviously, every path has to cross the cut. Right? It's sort of a generalization of this reachability argument that I was making here. Right? If the path doesn't cross the cut, then it can't get all the way to the T. Okay? And that means that the total value of the cut must contain all the paths. And so the theorem holds that the total capacity of the edges crossing that cut has to be larger than the amount of flow that's crossing the cut. Yes? Well, so cycles only help, right? So essentially what's going on with a cut and a cycle is that it eats up flow going out, but it goes away, it sends it back. So the net effect on the capacity of the cut is 0. Okay? So I should say, you can also prove this claim, right, about the value of the flow being less than or equal to the value of the cut by sort of algebraically, by summing the conservation constraints. Okay, if you sum the conservation constraints over all of the vertices on the left side, then you get exactly the same result. But again, I prefer the sort of combinatorial perspective on this problem. Okay? So now we have an upper bound that says that the value of any cut upper bounds the value of the flow. Well, I can take any cut that I want and make this argument. So what's the best cut for me to take if I want the strongest upper bound? Take the minimum value of an ST cut, right? So the best upper bound is the minimum value of an ST cut. Okay. And so what we've now proven is that the maximum flow value is less than or equal to the minimum ST cut value. And this is generally abbreviated to min cut under the assumption that we know what S and T are. Yes?
How do you know that that's the best upper bound?
It's the best one we can get from this theorem.
Oh.
Okay. But that's the next obvious question. Just how good of an upper bound is it? Okay, and some of you are grinning because you studied max flow before, but we'll keep going down this path. What? Oh boy. All right. Okay, actually, if we're finding that funny, we probably need a break. So 2 minutes. Okay. So continuing this sort of creeping towards the goal of finding the maximum flow, the next question I'm going to ask is, suppose that our flow is not maximal. No, not maximum. It's still not clear that we can prove this, but we're going to sort of try and figure out, again, we're not going to go straight for the maximum flow, but we're going to ask, how can we improve a flow that we currently have? So this is sort of connected to the how do you know that a flow is not maximum, right? So again, we're not trying to jump directly to finding the optimum, but it seems like a good step along the way would be to ask how we can improve a current solution into a better solution, because at least if you don't care about runtimes, that presumably will take you eventually to an optimum solution. Okay. So what would be the obvious thing to hope for if you had a flow that was not maximal, given the sort of analysis that we've been doing so far? And I say the obvious thing to hope for because unfortunately it's not going to be true. But what could we hope for? Yes?
That you can add a path.
That you can add a path, right? If you have this graph, you've got a flow that's using up some of your capacity. But if there is still a flow, if there's still another path from ST that has more capacity on it, well, then you can add flow on that path and improve the value of your flow. So it would be nice if whenever you didn't have a maximum flow, you could say that there was this path that still has capacity on it. Unfortunately, that's not true. So we can build ourselves an example. So I'm actually going to draw this as an undirected graph, but what I mean is both edges have 1 unit of capacity, so in both directions. Okay. And here's S, here's T. So suppose that my current flow is a path that goes like this. Okay. So this is a flow that is carrying 1 unit from S to T. Is it a maximum flow? Right, its value is 1. Is there a better flow that has a larger value? What should it do? 2 paths, right? The sort of upper path on the diamond and the lower path on the diamond, right? So this is not a maximum flow. But there's no path from S to T with capacity, right? Because I sort of foolishly consumed part of each path as I went. So this requires introducing the sort of critical idea that, and I think Ford and Fulkerson were the ones who noticed this first, that we're thinking about the wrong graph if we're looking for a path in this graph. Okay, so if we think about how we might want to sort of correct this flow to the maximum flow, what changes need to be made? So what do you reverse the flow where? Exactly. We want to take flow off of the middle edge, right? And instead, we want to add some flow, right? We want to put some flow on this edge, right? We know we need that. We also know that we need some flow on this edge. The problem is that we want to take flow off of the middle edge. We're not putting flow onto an edge here. We want to actually remove the flow from this edge. Okay. But if you look at these arrows I've just drawn, they sketch out a path, right? It's just not a path in the original graph. It's not a path that fits the capacities that I have in the original graph. Okay. But if I think about where what I want to do, that I want to remove flow from edges that are carrying flow and add flow to edges that are not carrying flow, this takes us to this fundamental notion of a residual graph. So given our graph G with its capacities U and some flow F, I'm going to define the residual graph G sub F by specifying new capacities, kind of pulled out of thin air, where I say that the residual capacity from V to W is equal to the original capacity from V to W minus the flow that is currently going from V to W. So that by itself seems pretty natural, right? I've used up some of the capacity, and so I have less capacity that I can still use. Where it gets interesting is when you think about the reverse direction. So what's happening in the reverse direction? So if I have this positive capacity from V to W, and I use up some of it to send a flow, what happens to the capacity from W to V? Well, the formal definition just says that it's equal to the original capacity from W to V minus the current flow from W to V, right? But what's the relationship between these two quantities? Well, it's skew symmetric. So in fact, this is just equal to the capacity from W to V plus the amount of flow going from V to W. Okay? And that represents something very natural. Okay? What it's saying is that, well, I had some capacity from W to V. It might have been 0. Okay? But I did have some capacity from W to V. But I went and sent some flow from V to W. So in a sense, that's giving me more capacity to send stuff from W to V. Because not only can I use all of the capacity from W to V, I can also undo some of the flow from V to W as a way to send, in a net sense, more flow from W to V. Okay? So that is the sort of key definition of a residual capacity, of a residual graph, where you increase flow not only where you increase the capacity to represent the ability to remove flow from the opposite direction. So actually, before I change pictures, what does the residual graph look like in this diamond? How much capacity do I have on each edge in each direction? Yeah?
So I have 1 in the bottom left.
Good. So here, I haven't used this edge in either direction, so it's still the same.
-1 on the top left. So if there is a arrow over there, right?
Over here, -1, in which direction?
It's -1 in this direction, so it's 1 of this direction.
So remember that we started with a capacity of 1, right? So it's not -1. We're generally going to avoid creating negative capacities, right? Yeah?
So that one was 0 in the travel, but 2 in the reverse direction.
Exactly.
And then its counterpart is the same.
Right. So here also we have 0.
Is just 1.
And what about in the middle?
In the middle, we're going to have the 0, 2 that we had from before.
So here also we have 2 and 0, right? So this is the residual graph according to the definitions that we gave. Now, what's cool about this residual graph is that if we think about the operations that we wanted to represent, that we wanted to do, right? Add some flow here, remove some flow here, add some flow here, right? There's a positive capacity path in the residual graph, right? 1, 2, 1. That corresponds to the edges that I want to change. And this points at the sort of key general theorem. Which is if, well, you have a non-maximum flow if and only if there is a path, positive capacity path. And so what we call that is an augmenting path. In the residual graph. Okay. And so here again, the theorem is relatively straightforward in one direction and takes a little bit more work in the other direction. So suppose that there exists an augmenting path. I want to argue that the flow is not maximum. How do I do that? Yeah?
Just add copy the path to the dish and then just add them. Just add it.
Yes, but add how much of it, right? How much flow? So I've got this augmenting path. What does that mean? That means that there's a path where each edge has positive residual capacity. U sub f.
construct the flow the same way in the residual graph, and then add that flow to the original graph.
Good. So that actually sort of solves the problem in its entirety. But if we just want to make an improvement, then instead of thinking about flows, it's simpler to think about paths, right? So I've got this path with positive capacity. How can I use that to improve the flow that I started with? Yeah?
Take the minimum capacity along the path.
Good. So increase f by the minimum of u sub f of e on each edge of the path. And that's sort of a compressed. It's saying find the minimum uf of e on the path, and then increase every edge on the path by that uf of e. Yes?
To get an improvement, you just need to have some add non-negative.
That's correct. Any positive number would do. And the point is, any positive number smaller than this number is still fine in terms of giving an improvement. But the point is that since, by definition, the smallest of these numbers is positive, that you can add a positive number, right? If the smallest of these numbers were 0, then you'd be stuck, okay? But it is a path of positive residual capacity, so you have this ability to augment. Now, we do have to check that the result is feasible, okay? So we have this f prime of e equal f of e plus, what letter should I use? Q. Q is a good letter. Where Q is equal to the minimum of UF of E's. Why do I still have a feasible flow when I do this? I'm starting to see the same hands a little too often. Everybody else get lost? So let's take it one step at a time. If I do this, if I add this quantity to every edge on the augmenting path, do I still have a flow? Let's not worry about the feasibility question, but do I still satisfy the conservation requirements? Sure, right? Adding on a path doesn't affect conservation. Because after all, I am computing, right, I'm adding incoming flow and outgoing flow to each vertex on the path. It doesn't change the net flow to the vertex. Okay? So the only question now is capacities. So did this change, did this increase in flow value on certain edges violate any of the capacity constraints? Yes, in the back.
It can't, because you're adding a both like the capacity has to flow through their own region.
Good. But we have to take this apart a little bit, or rather, we have to think carefully about these sort of skew symmetry issues. That remember, we have a positive f of VW in one direction. That means we may have a negative f of VW in the opposite f of WV. And we need to understand what that means in terms of summing the flow here, right? So the way I like to break it apart is to say, well, that if f of VW is positive. Sorry, let's do it a different way. So if the flow from V to W is positive and less than U of VW, then what are we doing, right? That's saying we put some positive flow from V to W. It's less than the capacity. But sort of by our definition, then still, when we add Q to that edge, we get something that's less than the capacity. Right? But for some of the edges on this path, we may actually be using them in the opposite direction, where they're negative, right? So if we have a flow, we're using it in the backwards direction, where it's less than 0. Okay. And we add this quantity Q. Okay, then what are we really doing? Then we are decreasing f of WV, right? When we add Q to f of, when we add flow to f of VW, we're decreasing the value, right? When we add flow to f of WV, because we're using the edge in the wrong direction, we're actually decreasing the amount of flow in the opposite direction from V to W. Right? Is this a problem? No. Because we've picked the minimum of the available capacities, this decrease will still keep our flow feasible. In other words, we may actually add so much to f of wv that it becomes positive, but in that case, we're in this condition where we've chosen a q that's less than the available minimum available capacity, and so the flow from w to v plus q will be less than the capacity from w to v. But in the opposite direction, we may actually be increasing a negative value, but that doesn't matter because we're still going to obey the capacity constraints if we're negative. Okay? So this shows us that if there is an augmenting path, then we can add a little bit of flow to every edge on a path and end up with a flow that has a larger value. Okay? Because in particular, we will have added capacity on some edge that's leaving S. So we will be increasing the flow out of S, which increases the value of the total flow. Now, what about the converse claim? So what if there is no augmenting path? Can we show that our flow is a maximum flow? Yeah?
So if we do the path decomposition and we take the cut that has the minimum capacity, then if there is not an augmenting, so if it wasn't a max flow, it would mean that there is actually an edge from the two groups.
Good.
That would mean that there is actually a path.
Good. So I think that what you just said argues a little bit more clearly, looking almost at the looking at the contrapositive. So suppose that there is no augmenting path. Okay. So what does that mean if there is no augmenting path? Well, that means that there is zero flow in the residual graph from S to T. Right? Right? So we just sort of switch our thinking from the original graph to the residual graph. In the residual graph, if there is no augmenting path, if there's no path in the residual graph, then there's no flow in the residual graph. That is the flow value is 0. You can't find a flow with non-zero value in the residual graph, because if you could, you would find a path in the decomposition of that flow, and this would give you an augmenting path. Yes? So if there's no augmenting path, there's 0 flow in the residual graph, and that implies, as we were arguing over there, that there is a 0 value, that there is an ST cut in the residual graph. Right? Which with 0 capacity. Right? That's the argument that we made over there. But what does that mean, having an ST cut with 0 residual capacity? Let's look at that cut. And now take it back to the original graph. So we've got this network. It has 0 residual capacity. So, I'm not going to draw the 0 capacity edges. We have a network that looks like this. And a cut here where every edge has 0 residual capacity. But what does it mean for an edge to have 0 capacity in the residual network? What is that saying in the original network? It's saying that it's used up, right? So 0 residual capacity, what that means is that f of e is equal to u of e on that edge. Right? Because the residual capacity is just the difference between those two quantities. Okay? So in fact, what we have is a cut where f of e is equal to u of e on every edge. Crossing that cut. Okay. But what that means, if we now do path decomposition, is that the value of the flow is equal to the value of that cut. Right? Because each of the paths out of S has to cross that cut. Right? And so the total flow value on all of those paths is equal to the total flow value, the total capacity of all of the edges crossing the cut. Okay. But if the value of the flow is equal to the value of the cut, what does that tell us? Yeah? It tells us this is max flow. How come? From the previous bound, right? We know that the max flow is no better than the value of a cut. So if it's equal, it must be maximum. Yes?
Where do we prove that the zero flow implies that there's a cut with zero value zero?
That was where we decide. That was over here when we talked about deciding whether there's a non-zero flow. Right? We said that there's a non-zero flow if and only if there's a path from S to T. And I'm simply applying that same argument to the residual capacities instead of to the original capacities. Right? So we have now proven one of the most celebrated results in combinatorial optimization, which is the max flow min cut theorem, which I won't bother writing by name because the theorem is the title. Right? The value of the maximum flow you can find in a graph is equal to the minimum value of any cut that exists in that graph. Yes?
If you have a flow, people would cut that as flow. Do we know that if you have that cut, you can make that flow?
Yes, but it will take a few too many minutes to explain given that I've already gone over time. I mean, we proved that, but I have to remind you why. So I'll do that at the beginning of next lecture. Okay? We'll be posting a problem set shortly. Look for it. Remember the optional lecture on suffix trees on Friday. Come, it will be a lot of fun, and I will see you on Monday.